today, so I'm not going to make that mistake again. Gotta love it, human factors error. Let me hide the thingy here as usual. All right, so I've got myself a little spreadsheet set up here to help you get started on homework 4. Piecewise slopes, based on a true story of changes in stress level as a function of proximity to law students taking a bar exam. That's the story for this homework, based on a true story, as I told you before. So I wanted to help you get started in building the pieces. Does that sound like a good idea? Yes, that would be good. Okay. So in this homework, there are 13 occasions of data. Does that sound correct? Good. I don't have all my homeworks memorized, but I'm going off of memory on this one. And I had instructed 3 different pieces. So there is a before period, which is from occasions 1 to 7. There is what I'm calling the immediate relief of having taken the test, gotten that over with. So there was an occasion 8 right after the test. And then afterwards, while you're waiting for your results, is from 8 to 13. So those are the distinct periods. So the idea is to carve up the overall 13 sets of occasions into these distinct periods and estimate fixed and random effects describing change within each of the periods. So, can you all see this okay, or do I need to make it bigger? It's good. Okay, I start to see people doing this. So I had instructed you to make occasion 7 the reference, right, for the intercept? So what am I telling you to do then with respect to how these 3 variables would be coded if occasion 7 is going to be my reference occasion? Yeah, this is a gesture question or a text box, chat box question. What are we doing? Zeroing them out. Yes, indeed. So the intercept for the model, where time 0 is, same concept, but now there's 3 different variables capturing change over time. So by putting 0 for all of them, then I will create session 7 as a common reference point. So then we figure out what goes relative to these zeros for each of these periods. So relative to 0, how many occasions back is occasion 6? What goes here?
Minus 1.
Minus 1. What goes here? Minus 2. Yeah. And in Excel, by the way, if you have a pattern like this and it will figure out that you have a pattern, you can highlight it and drag it. Nope, I don't want to move it. Of course, I can't do it while I'm talking to you, but you can drag down normally. I don't think I can get my mouse on the right spot, so I'll just do it manually. That's fine. So it would look something like that. Okay, with me so far? All right. So then if this slope right here, I'm going to make this bold so we can see it. And I'm going to shade that in to distinguish that as a reference point here. So if the job of this predictor is to capture change from occasion 1 to 7 only, then functionally speaking, I want to make it shut off after occasion 7 is over. And the way that I do that is to give it the value that it left off at where it shut off. So zeros then would go through the rest of the column. So the variable is dormant, so to speak, during this section. Okay, questions so far? No. All right. Likewise, these 2 variables right here, the second one is supposed to capture change from 7 to 8, and the third one is supposed to capture change from 8 to 13. So during sessions or occasions 1 through 7, they would also be dormant. So what goes in all of these boxes to make that happen? Big zeros. Yes, indeed. There we go. So let me move up so we can see this a little better. So to capture change from 7 to 8, then, what goes where my cursor currently is? In cell C9. Yep, because 8 is one more than 7. Now the tricky part. This slope needs to shut off because the third slope is going to take over. So how do I make it shut off? A 1. Yeah. It has to stay 1 because if I put zeros here, it would go back to where it was. So for all of these latter occasions, this slope has already had its impact, and so it stays where it left off. So then these two, this slope is active during that section. So we got that one done. And then last but not least, the third slope is supposed to pick up where the second slope left off. So that we have this one stays at 0. And what goes here? Yep, one more. So we got change over time in the usual way here. So section 2 of homework 4, there are like 6 questions that ask you for the value of your predictors. That's what I'm asking for. I'm checking to make sure that you have the logic correct of the coding. Now the tricky part will be writing SAS code that can execute this, or stata code, or R code. So I've given you some examples of what that would look like for the piecewise models in example 6. You can extrapolate that. I have also in the instructions for the homework put in a link to an example from 6242 that has 3 piecewise slopes for education. So if you follow that example, there'll be some code in there that you can take a look at as well. So at the end of the day, your data set should look like this after you've written the code to execute to make these 3 new variables. All right, any questions on that?
So if there is like one more section, such as like after 13th week to 20th, the category of after 8th to 13th would be 555 after week 13th?
Yes.
Okay, great.
Yes, exactly. If I had a follow-up period, then this would stay at 5 during the follow-up period because it's done. So the idea is that it captures the change and then it stops wherever it left off. And so long as you have balanced time like this, you can set up your new variables using just these integers. But if each person had a different set of occasions, like if the 13th occasion was a different time, then you would have to have variables saved in your data set as to when each occasion actually was, and you'd have to find it via subtraction. So there's an example, there's code in the syntax for example 6 that would demonstrate what that would need to look like instead. Okay.
Thank you.
Yes, thanks for the question. Any other questions? So then you should be able to add in fixed effects for each of these. And then I'm asking first for linear effects. So they would go in as quantitative predictors in the usual way. Then quadratic effects, but only for the 2 for which they are possible. So the middle variable here, this variable is functionally a dummy code. It'll either have 0 or 1. So there's only one possible kind of effect. It's the difference from 0 to 1. It can't have a quadratic effect, but the other ones can. So I would recommend having this table like handy as you're working on your assignment, because the values that you're going to have to put into the code for estimate lincom or contest statements to create predicted intercepts or linear slopes, the values that go into there are going to be based on the coding. So these constants that you're putting in, that's how you know what the value should be. Okay. Any other questions while we're on the topic? Homework? It's not due for like a week and a half, so you got plenty of time. The next thing due is a formative assessment on Monday, so just a little more review, and the questions, the latter questions on it are things we're going to cover today. Okay, we're good then? I can shut this down? Okay. Let me know if you change your mind and want to talk about anything. Then what we were doing last time then, we can pick back up. This is lecture 7A, trying to do a little bit of review slash stepwise progression through how you would approach modeling time. So what we had talked about last time were the steps that were common across all kinds of outcomes. So anytime you're addressing a longitudinal data set, you would do the following. Empty model first to make sure it actually is a longitudinal outcome. I would do the same thing for all of the predictors, by the way. So any variable that is measured repeatedly over time should have an intraclass correlation. The distinction of outcome versus predictor is conceptual, it's not mathematical. And the reason that I say that is the kind of variance that a predictor has is going to logically constrain the kind of effect that it can have in a model. So up to this point, we have had only one kind of predictor, which is time, essentially. Linear, quadratic, piecewise, exponential, what have you, but it's time. And in the cases that I've shown you thus far, time is a purely level 1 variable. It only has within-person information. And so what interclass correlation would it have if I tried to predict time as an outcome? If everybody has the same, say, 6 occasions of data, what would the interclass correlation be for a variable like that? Any guesses? I wouldn't ask if it weren't an answer that you could do with your fingers or type. Intraclass correlation tells us what again? Let's back up. What does interclass correlation tell us? Proportion of variance due to between. Yeah. So it's always between something. In longitudinal data, it's between person. In clustered data, it's between clusters. But between works as an adjective. So what are the possible ranges of an interclass correlation? What values could it be? Yeah, 0 to 1. Can't be negative because of the way the model's parameterized. So if the interclass correlation tells you the proportion that's between, and I have a variable like time, where everybody has the same values, does time have any between-person variation in it? Nope. So if time has 0 between-person variation in it, its intraclass correlation would be what? 0. Yeah. So logically speaking then, because time has no between-person variation, there is no way that it can have a between-person relationship with an outcome. Having variance at each level is a logical prerequisite to having an effect at each level. When would time have between-person variation? Whenever people differ at baseline in the time metric that you're examining change over. So if you're in grade schools and you collect data from 3rd graders, 4th graders, and 5th graders, and you follow them through middle school, that's an example of when your time variable for what grade they're in would have both within-person variation as the kids get older, as well as between-person variation in which grade they started in. So that would be 2 different levels of variation in a time variable in a design like that. Oh, captions, thank you. I forgot. Let me find that. Enable auto transcription, close the box, and hide it from myself so I don't lose my mind. There we go. Thank you. I forgot that. Now I got to double check that I'm actually recording. Okay, I did get that part right. Hooray. So designs in which people vary in time at the beginning are known as accelerated longitudinal designs, or cohort sequential designs is another term for those. That they are commonly used to try to cheat your way into a longer longitudinal study than you actually have time to do. And I say that in like a not like a bad way, but it's an approximation, because then like you have like if you followed your third, fourth, and fifth graders for 3 years, you have data all the way from third grade to eighth grade, even though you only have 3 years of data. So where that can go wrong potentially is in collapsing all of those children onto the same trajectory. If this year's fifth graders are different than last year's fifth graders, then which cohort they were part of needs to be a predictor in the model to differentiate them. So that's why I say, even for variables like time, for any variable that is measured over time, step one is to compute its intraclass correlation and to see what levels it has variance. That way you know potentially at what levels of the model it could be a predictor or an outcome. Okay. Does that make sense? Maybe? Yep. So then we talked about centering point. So where time 0 should be is an interpretational choice. It should be somewhere within the span of your data. And making pictures. So estimating saturated means on balanced data, or rounding time temporarily so that you can make pictures just to get a sense of what the shape of the trajectory looks like. And then from there, what would happen next depends on whether your data falls more on the change side of the spectrum or the fluctuation side of the spectrum. And so that was where we had left off last time. So any questions or parts that you want to talk about again that we did last time or before? No? We're good? Good as we're going to be? Am I frozen? I'm not frozen. Okay. Oh, there's some head shaking. There's some movement. Hello. Welcome back, everybody. We are all here today. It's Thursday towards the end of the semester, and damn it, we are going to make it. We are going to make it through. We are. One way or another, the semester will get over with, but we're not there yet. Closer, but not there yet. All right, then let's pick up on slide 9 here. So in the situation in which you have within person change, either because the study was designed that way, or because you accidentally measured something that changes as a function of days or years or weeks or what have you. So then the two questions you have to ask yourself is, what's going on average? And then to what extent do people differ from what happens on average? So what's going on average, that part is handled with fixed effects related to time. So what kind of fixed effects related to time do you need to accurately capture the trajectory of mean change across occasions? That's the question. And so there's lots and lots of options. There's continuous models versus discontinuous. So discontinuous being like the piecewise models that are good when you have discrete differences in what's happening over time, befores and afters, so to speak. Either of those can have linear or nonlinear change throughout each of the periods. We've talked about, we had polynomial examples. We used log time to approximate an exponential curve piecewise. There's 1,000,001 alternatives to this. I added some articles on your reference list for some other hacks in terms of nonlinear models for change that people have come up with, and they figured out a way to make SEM software or MLM software estimate them. So I added those additional things for your reading list. And in each of these cases, because these are fixed effects, because they are slopes of some kind, that a null hypothesis of 0 is plausible, and the slope could be positive or negative up to infinity, we can just use the Wald test that shows up on the output. We don't have to do anything different or special. So we take the estimate, divide by its standard error. That ratio is treated as a t or a z, t for denominator degrees of freedom, z for not, and then we get a p-value that shows up with that. So that's the relatively easy part. The part that is new this semester, the part that is incremental relative to general linear models, is the focus on the model for the variance. The idea of what else you need besides a single E residual that is supposed to have constant variance and no covariance. What else is in there? So you can think about this in a couple of different ways. Conceptually, I think the easiest way to think about it is which aspects of your overall mean trajectory do people need their own of? Do they start out at different places? Do they grow initially at different rates? Do they differ in how they slow down in their growth? So each aspect of the trajectory as defined by the fixed effects can vary across persons. And so we're asking, which of those growth terms do you need to make random in addition to fixed? So random is the deviation from the fixed effect. They go together. If you have a random effect in the model, the fixed effect that goes with it should stay along for the ride. So individual differences as a substantively meaningful idea. So we're asking, in how many ways do people differ from each other, and how much of the variability then in the data is because of that? So we get a number, we get a variance component estimate that tells us, the intercept variance is 10 and the slope variance is 2, and that's our new baseline for adding predictors. So this whole process is working towards building what is known as an unconditional model for change, or an unconditional growth model, meaning we figured out all of the terms that need to be in the model with respect to time. That is then a new baseline against which to judge how predictors can capture each of those distinct sources of variance. So it's an important intermediate step to get to the point where you have the best model for change in terms of all the stuff that you need and not the stuff that you don't. But just as the psychologist in me would talk about individual differences and inter-individual variability and all of those things, the wannabe statistician in me, I say wannabe because I'm not actually a statistician. As we've discussed, I'm a psychologist who masquerades as a statistician. The wannabe statistician in me is like, no. We're not answering questions about individual differences. We're accounting for dependency. That's what we're doing. We are allowing a pattern of correlation among the residuals from the same person and a pattern of heterogeneity of variance across time. That's what we're doing. We're doing that at the same time. So whether you look at it as solving the nuisance that is dependent data, or an opportunity to examine individual differences, it's 6 of one, half dozen of the other. So anytime that you have observations from the same something, random effects allow a correlation to occur in the data that better fits what's actually happening in the data. So that becomes the new assumption that you're making. Say the E residuals are no longer related after controlling for the random intercept, the random time slope, the random acceleration, etc., etc. And so this aspect of the model then has to be tested differently. We can't use Wald tests for variances because variances can't go below 0. So the idea of comparing a variance with a normally distributed sampling distribution where you can only have the positive half makes no sense. So instead we do likelihood ratio tests. We take the -2 log likelihood from a model that has only the fixed effect, and we compare it to the -2 log likelihood of the model adding the random effect in addition to the fixed effect. The difference in -2 log likelihood we treat as a chi-square, and the number of parameters that we added is the degrees of freedom for the chi-square. So that's all of that stuff. And then the third point here, do the residuals show any covariance after accounting for random effects? In certain contexts, you still may have some kind of residual correlation of occasions that are closer together in time. And so you can add that to your R matrix. That's where an autoregressive correlation or a Toeplitz correlation or something like that would allow the residuals to be correlated in addition to the correlation that's induced by the random effects. So those are all empirical questions to be answered with likelihood ratio tests in a given data set. Okay. How are we doing? Look, I'm not even having caffeine. I've switched to Diet 7-Up so that I can keep my energy level somewhere below a crazy person. Is this making anyone think of real data that they get to play with? No? Maybe? No, but I would like to hear about real data. Yeah, real data is something. I have some stories that I had forgotten I had made for a different class that I was thinking of bringing up once we get to the predictor part. So I will tell you some more about some real data from my past and arguments that I've had with people about it. So growth experiences and fighting with reviewers and stuff. That will be coming. All right, so this is my general strategy if I am modeling longitudinal data in which there is within person change as a function of some aspect of time. So then the end result of this process of building an unconditional model, testing fixed effects, testing random effects, is that I then emerge with a new baseline in terms of what is to be predicted. So for instance, if I have a random linear time model, so where we ended up, say, in example 5, then I have 3 different kinds of variability for my predictors to capture. I have between person variability in the intercept and in the time slope. So why do some people start out higher than others? Why do some people change faster than others? Those are going to be predicted by time invariant predictors. That's where we're headed today. And then the E-variance. Why are you off your line today? The only way to capture within-person variance that remains after controlling for time is with time-varying predictors. So we have these multiple variance components. We go about the process of adding predictors to the model that are designed to tackle each of these with distinct sets of fixed effects. So it's a very purposeful way of looking at which predictors and which effects should be included. But what if you don't have change? What if it's purely fluctuation? In that case, your model for the means may not need any fixed effects of time at all. The means may not differ over time, and that's fine. You can have a model that looks like that. The model for the variance, though, for the same reason, if people don't change, random slopes related to time are not going to do you any good. So this is where the family of alternative covariance structures then would be more useful. I personally like the idea of a random intercept as a starting point to allow individual differences in a level of an outcome, and then some kind of correlation pattern in R to allow residuals that are from occasions that are closer together to be more related, which is a very common thing. And so we can do likelihood ratio tests between nested models. We can do AIC and BIC for supporting evidence as well. So in that case, we end up with something that looks a little bit different. So in the alternative covariance structure models, there were 2 main kinds of families. There was R only and then R and G. Do you remember this? This sound vaguely familiar? There were R only models and then there were G and R models. And in the R only models, all of the variance and covariance was in the R matrix in one place. And in the R and G models, it was in 2 places. So you could end up, in theory, with an unconditional model for time that is R only. Let's say you use a full order Toeplitz, that could work just fine. And in that case, you'd only have 1 pile of variance because you're not using random effects to partition the variance to create a pattern. You're just allowing it to be there. So there's nothing wrong with that, but that does change then the strategy of how you would think about variance accounted for. It's a different strategy if there's only 1 pile as opposed to multiple piles. So it gets a little tricky to talk about R-square in such cases, but it is still technically okay, so long as the dependency in the data is being modeled. That's the key thing. So then why is it week 10 in this semester or week 11? Anybody know? Week 10 or 11, we're somewhere in there. That's what I know. So you might be asking yourself, why is it that we're in week 10 of the semester and we haven't even gotten to predictors yet? That is a valid question. here's my logic. So we start with this in layers. So we start with fixed effects of time because that's the anchor point for the random effects. The fixed effects are what the random effects are varying around. The random effects then have variances that characterize between person difference. And those between person differences are what the time invariant predictors have to account for. So those person level predictors, which we're starting today, I promise, have to be specified as a function of what random effects there are in the model. So if people don't change differently, it doesn't really make sense to put in an interaction term of time with a predictor that would ask whether people change differently as a function of predictor X. If you didn't find out that they changed differently in the first place, then there's not much for that term to do. So there's a logical ordering as to what would be plausible and allowed to be tested in these cases. Once you have your time invariant predictors, generally then we would go to time varying. And then those are supposed to soak up whatever variation hasn't been soaked up already by time and the time invariant predictors. So this is all to say that the fixed and random effects of time logically constrain what there is for the predictors to do, which is why they come first. And the wannabe statistician in me would remind me that, hey, the standard errors for your predictors are only going to be accurate to the extent that your dependency is modeled appropriately. And in longitudinal data, time-related dependency is the biggest thing. It's a very tricky thing to model, and so it takes more consideration than in clustered data. So this fall I'm teaching the clustered version of multi-level models. I noticed a few of you are going to come play, right? We're going to have a good time? Yeah, we are. In that class, I go straight from what is an intraclass correlation to let's get some predictors in there. I get to skip 8 weeks of material because there's no time. There is not as much consideration as to how people correlate differently because people are treated as exchangeable. But which occasion is which is not usually exchangeable. So time introduces a lot more complexity into the patterns that have to be modeled in this context than in a people within groups context. So there's a lot of new stuff, I would say, that I have a chance to get to in that class that I can't get to in this class because time takes up so much time. But that's the way it is, which is why I used to do it as 2 semesters. So then the steps, these are just some slides to make a suggested stepwise sequence of how you would add terms to the model. So this is for polynomials on this slide, 14. Yeah, so you did this in homework 3. For piecewise models, you'll get a chance to practice this in homework 4. And that's the end of the review. Okay, questions or comments on any of that? So you ready to start painting with me now? Finally, we're going to start painting? Well, I have to break your heart first before we can start painting. I have some bummer news about time varying predictors that I have to address first, and it's with respect to missing data. So I'm switching to lecture 7B here. We're going to start talking about time varying predictors. Thank you. I'm glad you liked the review. So first off, what happens to missing predictors? Because I want you all to recognize that this is not good. So in longitudinal data, people don't cooperate. Sometimes they don't come back. Sometimes they don't answer all the questions. Incomplete data is pretty much a given. So there's lots of reasons for it. If you're planful about it, then you have a better shot at getting the right answers even with missing data than if you're not planful about it. But people don't cooperate and you can't really plan for that. So the goal of any approach to addressing missing data, incomplete data, the goal is never to fill it back in. Some of the approaches actually do fill in the missing data, but that's not the point. The point is to try to get the right answer for what the parameters would have been had the data been complete. So strategies of filling in the missing data are a means to an end, they're not the point. And so you will often hear people talk about ways of addressing missing data. Never ever on that list is something called mean replacement or conditional imputation, where it's 1. Have you been told this, right? Never ever. You cannot fill in the missing data with a number and treat it as if it's real. That is straight up cheating, and it is not cool ever. Either of those is going to greatly reduce your residual variance because you're plugging in a prediction for what the missing data should be. So that part's not cool. Preferably not is listwise deletion. Dropping cases that have missing information is a reduction in power at a minimum and potentially causes bias in terms of who those people are. So whenever the data are missing for reasons, then it hurts your analysis to not have those cases in the model. So then people talk about how missing data can be handled. And there are 2 main families of approaches: full information maximum likelihood or multiple imputation. So full information maximum likelihood is what we've been doing this whole semester. The term full information means that the likelihood function operates on each individual data point. So in these models, the algorithm searches for the right answers for all of the random effect variances and residual variances and all the variance model parameters. And once it has those answers, it gets the fixed effects. And then it uses those numbers to calculate the height of each person's data. And then the log of the height gets added together, and that's your model log likelihood. So FIML, as it's known, full information maximum likelihood, REML is also full information. But for whatever reason, FREML is not a thing, whereas FIML is a thing. So we've been doing that the whole time. Multiple imputation is a process of filling in the missing data with predicted values, but critically not just doing it once. You essentially create a regression model that predicts what the missing value would have been for every variable that has missingness. Then you add an error term. So you're not filling in a perfect prediction, you're filling in a noisy prediction. And then you get another data set and you draw a different error term and fill that in. And then you get another data set, draw a different error term and fill that in. And so you would end up with somewhere between like 5 and 100 versions of the same data set, each with a different filled in predicted variable that has error to it. And so then what you would end up doing is analyzing all of the data sets separately, pooling all of the results with special formulas, and then you get your final set of results. And now you're all glaring at me. I'm not going to make you do this. It turns out that multiple imputation is very tricky for multi-level data because it's very hard to anticipate all of the ways that all of the effects that you would want to put in the model have to be in the imputation model. Modern software, though, does a lot of the hard work for you. So like in M+, for instance, you can tell it that type equals imputation. You give it a text file that has the names of all of the data sets, and it will run the same model on all the data sets, pool the results, and spit out one output file. There's various programs in R to do this. There's, what is it in SAS? Proc something. There's an imputation thing in SAS. I forget what that is. So I honestly have never done a multiple imputation to address missing data because I always try to throw full information maximum likelihood at it. Both of these methods assume something called missing at random, which is random conditional on the data that you do have. So we have a question. Can I deal with missing data without generating different data sets using FIML? I prefer that over multiple imputation. Yes, I prefer that too. Yes. The answer is yes with an asterisk. So here's the dirty trick about full information maximum likelihood and what you can and can't do with it as a function of software. So here are the designations with respect to missing data. There's completely at random, which is what it sounds like. At random, which means conditionally random. All of the missing data techniques assume that one. And then there's missing not at random, which is probably true, but if that's the truth, you're screwed because you don't have the information and you can't do anything better. Now, how full information maximum likelihood gets applied in multi-level models depends on your software. There's a lot of misconception about what happens in multi-level models in particular with missing data. Here's the bad news. The rule is in proc mixed, stata mixed, R-Elmer, all of these packages, every row that is complete in your data set gets included, and any row that is missing anything does not. It handles it by dumping cases. Now, I know that sounds surprising, but it's an occasion-specific dumping of cases. Because in these models, in the stacked data set, it's one row per occasion per person. So if I have somebody who has 4 occasions worth of data, and I missed one of my covariates at time 3, then I keep occasions 1, 2, and 4, but I drop occasion 3 for that person. So it's better than the listwise deletion that is person level that ordinary least squares enforces, but it still doesn't solve the problem that it's functionally listwise deletion. And why we haven't really talked about this up to this point is that if you have an outcome at a given occasion, you probably have the time predictor for that occasion. You know when it happened. But for predictors that are measured repeatedly, that may not be the case. So if you are going to not do anything about your missing data, be prepared to drop the cases that have missing information. That's just what's going to happen. And for that reason, I would recommend pre-selecting your sample just to the rows that are complete on all the variables you're going to look at. That way your sample size stays consistent across your analyses. And more importantly, your -2 log likelihood, AIC and BIC are all on the same scale. Because -2 log likelihood, like log likelihood is literally the height of all the cases. And if you have a model where some of the cases get dropped, you're going to have less height. So if you ever are in a situation where you're doing a -2 log likelihood and you see that it drops significantly, but the thing you added to your model is not significant, that should be a dead giveaway that you dropped cases. So the heights are only comparable if the cases are comparable. But not everybody wants to drop cases with incomplete data. So you've only got a few options as to what happens. But I wanted to demonstrate this briefly here. So if I have this wide data set, so this is what happens in, say, repeated measures ANOVA is what it would look like going into that, versus what we've been working with in this stack structure. So if I have a model here that I have unconditional, so just time predicting the outcome variable, then I get to use rows 1, 2, 3, I get to use 5, and I get to use 8, because I have time and DV. If I add in my time varying predictor, then I only get to use rows 1 through 3, 5, and 8. If I add in the person predictor, here's the bad one. So if you have a time invariant predictor that is missing, your whole person is gone because all of their rows would be incomplete. And if you have multiple variables, each with distinct patterns of missingness, you can get into like a Swiss cheese kind of situation where there's a lot of holes in the data, and when you try to correct for it, there's not a lot of data left. So this is a bummer, right? Listwise deletion is a bummer. But I thought FIML handled missing data. No. Not in this context. It only allows you to use whichever occasions are complete. That's the rub. So then what do I do, Lisa? I don't want to dump all my cases. I'm glad you asked. So there are 2 strategies that can be used to address this problem, and they each require switching software. So the idea of using FIML in a multivariate context is one way to solve this problem. So if I estimate the exact same model that we've been talking about using mixed in a structural equation modeling package, you have the option to tell the program that the predictor is an outcome. It's a hack. It's a trick. More formally, what you're doing is bringing that predictor into the likelihood so that it's a joint likelihood of the predictor and the outcome, as opposed to just a conditional likelihood just predicting the outcome. So then the parameters of that predictor, its mean, its variance, and its covariance, are things that get found as part of the likelihood process, and you can have missing data. Well, that sounds great, right? Let's just do that. Except, anytime that you turn a variable into an outcome, you have to give it a distributional assumption. So one of the nice parts about having predictors is that they have no distributional assumptions. They could be binary, they could be skewed, they could be continuous, they could be whatever you want, doesn't matter. If they're not predictors anymore, if they're treated as outcomes, then they have to have some kind of distribution associated with them. And in most cases, it's multivariate normal. So if I have a variable that has 3 groups in it, for instance, do you think that's ever going to be normally distributed? Nope. And you can designate different distributions for variables, but then they really do have to be outcomes. They can't be predictors. So it's a limitation in terms of what FIML can do. You can have predictors with missingness, but at the expense of having distributional assumptions for them. And that will matter more if there's missing data. So then, what about that thing that was a lot of work, multiple imputation? That is an active area of research, how to apply multiple imputation to these sorts of models. It's not as easy as you would think. Not only do the variables that have missing cases also have to have distributional assumptions, because imputation treats them as outcomes. It's the same idea that they're back in the likelihood. But in order for the results of your eventual model to be correct, your imputation model has to anticipate every possible effect that you would want to look at. Fixed effects and random effects and interaction terms and nonlinear terms, and you can't put all of that in at the same time. So if you build an imputation model that lacks certain features, when you use those completed data sets in the analysis, you're not going to get those features back. So it's very tricky. So I am sort of punting on this for the purposes of these examples and saying I'm pre-selecting my sample so that everybody has complete data, but know that there are these other options for you. And the Piles of Variance website for the book has M+ code for all of these models, in which one of the things you could do, because it's an SEM package, is bring the predictors into the likelihood. So if you estimated the exact same models that way, then you could have missing data. I think the same is true of Levon. I believe in R because I think it has a multi-level component to it nowadays. So the bad news about missing data, it doesn't get handled. Complete rows only. All right, questions on any of that? Now we get to paint. I'm sorry to have bummed you out, but we're going to paint now. And put some predictors in the model, finally. So time invariant predictors is what we're talking about. Level 2 predictors. So these can be things that you care about deeply as a predictor, or they can be controls, things you don't care about, but someone else will yell at you if you don't put it in your model. To me, that's a substantive distinction that I don't make. I call them all predictors. So they're X's. Time invariant predictors are person characteristics. They are level 2 predictors, and they are things that you have only measured once. So time invariant is a consequence of your measurement schedule, not a statement about the variable itself. So oftentimes people try to save time in longitudinal studies by collecting a bunch of stuff at baseline and then never asking those questions again. And they are making an assumption that those variables didn't change over time. So that may or may not be the case. So if it's a construct that may have changed over time, but you didn't measure it over time, then you would want to narrow your inference accordingly. So if I have data across adolescence, I'm measuring kids from, say, 10 to 18 or something, and I only ask parents about their various attitudes and strategies at the beginning of the study, I can't really talk about the effect of parent attitudes as a variable because I don't have that. What I have is parent attitudes at age 10. And so just keep in mind that like time invariant is a consequence of how many times you measured it, even if it is a trait that could change over time. If you measured it once, it's time invariant. So time invariant predictor is sort of the accepted nomenclature. Person level variable, between person predictor, level 2 predictor, all of those terms go together. We are going to center all predictors so that 0 means something. It is very common to center continuous predictors at the mean. That's known as grand mean centering. That's fine. You don't have to pick the mean though. You can pick any value that is meaningful in the context of the scale. So for instance, there's a data set that I used to work with that had years of education, and like the mean years of education for the adults in the sample was something like 13.82. No one wrote that down. Like 13.82 years was not an answer given by any person in that study. I can guarantee it. So if I want to talk about the reference for the model, like the "you are here" sign for what my parameters are going to do, like the average person doesn't really correspond to anyone in my data set. So I might center education at 12 years instead so that my reference person is someone with a high school degree. It's within the span that's observed. It's totally up to you because it's just an interpretation thing. If you have a level 2 predictor where 0 is already meaningful, like, number of times you've been hospitalized or number of chronic conditions you have diagnosed, like something like that, leave it at 0. It's fine. For categorical predictors, you have to choose whether you want the software to carve them up for you or whether you want to do it yourself. And then you have to know what happens in terms of your software as to who the reference group is if you let it do it. So by default in SPSS and SAS, the highest category is the reference. By default in Stata and R, the lowest category is the reference. You can change it relatively easily in the latter two packets though. So what do these predictors have to do? If it is a model for change over time, they adjust the growth curve. So for instance, if I have time as my x-axis here, and I have an outcome y over here, and I may have people that are high on my x level 2 predictor and people that are low on it. If I put in a main effect of my time invariant predictor, that would allow a result like this. Main effects shift the intercept up or down, the same way that they do in regression models. So if I put in a main effect of x, then I would talk about the change in the intercept for a 1 unit change in x. And that would imply that the effect of x is constant over time. The same effect of x happens at every occasion. So it just corresponds to a shift in intercept. You could have something like this, where you allow an interaction between your time invariant predictor and time, and that changes the story. You could have something to where x doesn't appear to have an effect at the beginning of the study, but it does have an effect by the end, because what x is actually doing is changing the rate of change, not the intercept. So I have here main effect of time question mark. In order to know what the main effect of x, or main effect of x question mark, in order to know what that means, you have to know where time is centered. So if time 0 were here at the beginning of my growth curve, I probably wouldn't have a significant effect, main effect of x, because it's a conditional main effect. If time 0 were at the end, then maybe I would have a significant conditional main effect of the predictor, because it's wherever time 0 is. And then you can have something that looks like both. So bottom line, you can think of time invariant predictors as moderators of the growth curve. It makes the slope faster or slower as a function of the predictor. It makes the intercept higher or lower. And you have the potential to include moderation of each aspect of the growth curve. So if you have a random linear slope and a random quadratic slope, for instance, the time invariant predictor can moderate each of those because people need their own. Why do they need their own? Because of the predictor as one of the explanatory variables. With me so far? If you have a fluctuation model, the story gets a lot simpler. If there's no time, then there's nothing for the time invariant predictor to do other than bump you up or bump you down. There is something else that time invariant predictors can't do, and so I wanted to give a nod to that, although I don't have time to talk about it this semester. It's in the book. And the other thing that time invariant predictors can do is allow heterogeneity of variance. So these are specific variants of multi-level models that are known as location scale models. That's the term you should ask the Google about. The person you should ask the Google about for this, by the way, is Don Hedeker, the University of Chicago. He wrote the software that does these models. He invented them, as near as I can tell, and he's like the man. But to give you a sense of what this would be, like let's say that I'm looking at growth in inches. Let's say literally growth, right, of children. And let's say that I have a model in which children grow at different rates. So some kids are shorter or taller than others. Some kids change in height more quickly than others. And maybe I have a hypothesis that gender is related to that. Maybe I want to say that boys start out taller and grow more. Possible. Depends on what age we're talking about, but that could happen. So if I put in my gender predictor as a time invariant predictor, fixed effects in the model for the means, the main effect of gender would allow boys to start out higher or lower. The interaction of gender by time would allow boys to grow faster or slower on average relative to girls or relative to whatever other groups I have. But in addition, what if I had a hypothesis that boys are more similar to each other than girls? Could that be? That people with some characteristic are more similar to each other than people with other characteristics. Yeah, that could be. Like if I had people who were not addicted to drugs versus people who have a history of addiction. There might be a lot more variability amongst the people with a history of addiction than the people without a history of addiction. So there may be questions about heterogeneity of variance as a construct. You can think of it as variability across people, or you can think of it as inconsistency over time. Residual variance is functionally inconsistency. So in these models, you could also allow different G matrices and different R matrices as a function of these predictors. So you could say that for a 1 unit increase in my predictor X, people become more variable from each other by this coefficient. That's the idea, is that you can have predictors of differential variability as well as differential mean trajectories. And so these models are harder to estimate. I have some examples in the book that uses SAS-NL mixed. They were recently implemented in M+ using something they call a log V parameterization. You need Bayes to do that, of course, in M+. Otherwise, you can throw these at maximum likelihood, and they are tricky to estimate, but there are certain situations in which they make a lot of sense. So that's one other thing time invariant predictors can do. As an example of a fluctuation model, so in a fluctuation model, something like a negative affect every day for a month. What if I had that as a variable? So some people are grumpier than others, am I right? Like just as a trait, right? And some days are worse than others, am I right? But then if we think about how people behave, there are some people who are moodier than others, meaning they fluctuate more in their negative affect, and there are some people who are more chill. They might stay constantly grumpy or constantly happy, but they don't fluctuate as much. These models, by default, give everybody the same residual variance. These models, by default, say everybody would be equally moody. That doesn't seem very plausible. So you could put in predictors that say, I think that older people are going to be moodier than younger people. So I'm going to put in age as a predictor of the residual variance, the amount of inconsistency over time that people do. So these sorts of models are useful in things like studying drug adherence, like the consistency with which you take your medicine, the consistency with which you get exercise every day, ways in which like the idea of consistency corresponds to lack of variance, but inconsistency corresponds to residual variance. So there's a lot of context in which you might have hypotheses about variability. And I have a paper from 2007 looking at this in patients in a nursing home, looking at affect and variability in affect, and people who had worse cognitive scores were moodier than people who had better cognitive scores in the nursing home. The downside is that I did not include the appropriate random effects in the model for the variance, and so that paper is probably wrong. So don't use that paper, use the other ones. I haven't actually done the analysis to verify that it's wrong, but I'm about 90% certain that it is. Because it was the best I knew how to do in 2005, and I didn't know any better. So there's my history. I can give you some readings if anybody's interested in hearing more about this, but just put a pin in that this is another thing that time invariant predictors can do. What they can't do, though, is have random effects. So for instance, let's say that I collect biological sex as a level 2 predictor, and I collect it once. So I've got a blue dot and I've got a pink dot here. I can't make a slope through each of these dots, the same way that I can make a slope through the dots at each occasion for a time varying outcome. So level 2 predictors can only have fixed effects in these models. They cannot have random effects. The only way that they could have a random effect is if there was a level 3. So for instance, if I sampled children from different schools over time, then in theory, any gender differences that I observe could differ over schools. But without that extra level, the level 2 predictors can't have random effects. They, technically speaking, when you put them in a location scale model, you end up with something that's kind of like a random slope. So I have this caveat here, but conceptually it doesn't work. People can't have their own of something that's only been measured once for them because they are constant, not a variable. Yes, and neither did the people reviewing. Not only did the reviewers not know that I was wrong, I got the Article of the Year award from that journal. I shit you not. I have a little trophy in the office at work that I never go to. That Article of the Year. Wrong. True story. 2007. Yep. Multivariate behavioral research. Thank you very much. So, anywho. So what would a time invariant predictor then look like in the models that we've been talking about? For a point of reference, let's use a random quadratic time model. So a model where each person gets their own intercept, they get their own linear time slope, they get their own quadratic time slope. Because people differ from each other in 3 ways, there are 3 things that any time invariant predictor could do. So if I use education as a time invariant predictor, so I'm thinking about like a study of adults or older adults where education would be like they're done, they're not going back to school. It's time invariant. If I put in education as a main effect in the model, that is asking whether it moderates the intercept. Do people with more education differ in their level of an outcome? If I put in education as a moderator of the linear time slope, functionally speaking, that occurs as an interaction term. Education by time then answers the question, is part of the reason why people need their own time slopes because of education? And likewise, if I want education as a moderator on quadratic time, that is education by time squared. Is part of the reason why some people decelerate more than others because of their education? That would be the answer to the question. So the equations would look a little something like this. So I have added in those three effects into this model of education, abbreviated ED here. So the level 1 model is exactly what we've been talking about up to this point for a quadratic effective time. So I've got beta 0 as my intercept, I've got beta 1 as my linear time slope, and I've got beta 2 as my quadratic time slope. Each of these betas has an I subscript because each person is going to get their own version of it by making this beta an outcome in its own level 2 equation. So because I have 3 betas, I know I have 3 level 2 equations. The beginning of the equation and the end of the equation you've seen before. So gamma 0, 0, gamma 1, 0, gamma 2, 0. Those are the fixed effects. So gamma 00 here is the fixed intercept. Up to this point we had said it's the fixed intercept, which means it's the predicted mean at time 0. But now because we've added another predictor, it's also at education equals 0. So if I center education at 12 years, for example, then gamma 0, 0 tells me the predicted outcome at time 0 for somebody with a high school degree. Gamma 01 is my fixed effect of education as a main effect. So if you look at the subscripts within this beta 0 line, the first subscript is a 0 in each case because each of these terms is predicting beta 0. So the first subscript is which beta does it go with in the level 1 equation. So the first set of subscripts are all 0 for this first line. The second line here, the first subscript is a 1 because these all go with beta 1. And the first subscript is a 2 in the last row because they all go with beta 2. The second subscript is an index for which predictor it is within the level 2 equation. So this is gamma 01 because education is the first predictor of beta 0. If I added in a second time invariant predictor, it would be gamma 02, gamma 03, gamma 04, gamma 05. So the second predictor, second subscript we haven't really needed up to this point, now we do. Okay. U0 then. Same idea, slightly different take. Previously, without education in the model, U0 would have been how far off my intercept is from the fixed intercept. Now U0 is how far off my intercept is from the intercept predicted by education for me. So this model says that everybody who has 12 years of education has the same intercept. But not everybody with 12 years of education is going to have the exact same outcome. So U0 is leftover reasons why some people need a different intercept after controlling for education. That idea of U0 being leftover deviation, sometimes people call it a level 2 residual because it's leftover. I find that confusing, and so I don't use that term. So I just call it random intercept leftover. All right, how are we doing? Thumb sideways. Okay. So this is a linear effective education, given the way that I specified the model. So gamma 01, what that number is going to mean is it is the change in the intercept for a 1 unit change in education. Could I have a quadratic effective education? Sure I could. Could more education not help after a certain point? Sure I could. If I wanted to do that, I could add education squared as a second predictor, and it would be gamma 02. So that is to say that all the stuff that we paid attention to in terms of nonlinearity with time should also pay attention to that with any quantitative predictor that's not time as well. All right, so it's 3:12. That means it's about time to wrap things up here. Any questions on what we have so far that I can help you with? All right, in that case, please remember to do your formative assessment by Monday night so we can go over it on Tuesday. Let me know if you need any help with homework 4. And office hours start now. Thanks for tuning in. Have good weekends. Hang in there. And I'll see you next week.